Hello everyone. So I will talk about stability and I will directly dive into the topic, right? If you remember Lyapunov's stability theory, or in general energy functions, consider a positive definite energy function. At zero, it is zero, so it contains the origin, and V is radially unbounded. So we are talking about an energy function like this, for example, let's say x, V of x, something like that. As x goes to infinity, V goes to infinity. This is what we mean by radially unbounded. In this video, I will mainly talk about global stability, and we can cover local stability in another video. All right, basics. So when you have a positive definite energy function, let's say you are differentiating it, if you have this, then this means your system is Lyapunov stable or global Lyapunov stable, meaning that your trajectories are bounded. They won't diverge to infinity. If you have this sign, when you take the derivative, you have asymptotically stable system, meaning that as t goes to infinity, x going to zero. To have exponential stability, you need a form like this, because in this case, v is upper bounded by this, so it converges to zero at an alpha rate, and I'm going to talk about more about this later in examples. And if you end up having a constant term, and this is also another positive constant, this was also positive. This can be positive or negative, but we are going to find it from upper bound, so it is positive. In this case, you have boundedness. Your V will be upper bounded by this, and after this time passes, alpha is positive, you converges, the trajectories will converge to that bound, so you will be trapped inside that bound. In this case, we say the state is bounded. And basically, to obtain this form and this form, we are going to use comparison principle. I'm going to talk about that. And I'm going to also talk about when you have this Lyapunov stability, we should check Barbalat's lemma or invariance, LaSalle invariance principle, to see if we have more than Lyapunov stability. And these are the old textbook concepts. I will dive into examples and illustrate each stability in detail in the context of several examples. So let's do it. All right. For the first example, let's start simple. Let's say x1 dot equals to minus x1, x2 dot equals to 0. Well, of course, you don't need a energy function or Lyapunov function to analyze this, right? You can look at the solution. If you solve this, this will be x1 of t is e to the power of minus t x1 0, and from here x2 of t will be x2 0. So in this case, x1 goes to 0, x2 remains constant, so bounded. So we are looking here a system in general, but if we consider both states, it should be Lyapunov stable, but can we show also x1 goes to 0. So let's consider the Lyapunov function candidate or energy function, x1 to the power of 2, x2 to the power of 2. It is positive definite, radially unbounded, it contains the origin. V dot is simply 2x1 dot plus 2x2 dot. Inserting these to here, we have minus 2x1 to the power of 2. Since we don't have a second term, the best we can say is this, nothing more than that. If you also had a term like minus x2 to the power of 2, or minus x4, minus 4 minus some positive constant multiplied by x2 to the power of 2, then you can say less than 0, but this is not the case. You only have one variable. You don't know what the other variable is doing. So you have here Lyapunov stability, or x1 and x2 are bounded. All right, this is what basically Lyapunov stability theory gives us. But if we simply observe this equation, something more going on. x1 is not only bounded, but it also goes to 0. So from here, can we capture this? To capture this, basically we use Barbalat's lemma. How we can get more than boundedness of x1 and x2. Barbalat lemma says the following. If v dot dot bounded, then v dot goes to 0 as t goes to infinity. Simple. So if we show v dot dot bounded, then v dot goes to 0. What is v dot? Minus 2x1 to the power of 2. Then x1 goes to 0. So let's look at v dot dot. It is basically minus 4 x1 dot, which is minus 4x1 minus x1, or 4x1 to the power of 2. Now here we already established x1 is bounded. So this is bounded coming from here, coming from Lyapunov stability. If this is bounded, then v dot is bounded. Then v dot goes to 0. What is v dot? This guy. So from Barbalat's lemma, then, limit t going to infinity, x1 is 0. So we have slightly more than Lyapunov stability. All right, so thanks to the Barbalat's lemma. x2 is bounded. So conclusion is x1, x2 bounded, and x1 going to 0. Now, let's say you have a term, a constant term, let's say some d here. In this case, we know that if you solve this, right, x2 will go to plus minus infinity as t goes to infinity. Okay, so if this was the case, let me erase everything. So I converted the example to another example. Then we have here 2x1 minus x1 plus 2x2d minus 2x1 to the power of 2, 2x2d. This is certainly not less than equal to 0, right? This can, you don't have a good term here. And you don't need to proceed further in this analysis, so you cannot get anything out of this. I just wanted to mention about that. All right, so let's move into another example to illustrate the concepts. So let's say you have x1 dot equals to minus x1 minus x1 x2, x2 dot equals to x1 to the power of 2. All right, let's consider a Lyapunov function, x1 to the power of 2, x2 to the power of 2. It is positive definite, radially bounded, it contains the origin, all same stuff. V dot is 2x1 x1 dot plus 2x2 x2 dot. Inserting them to here, we have 2x1 minus x1 minus x1 x2 plus 2x1 to the power of 2, which is 2x1 to the power of 2 minus 2x1 to the power of 2x2 plus 2x2 x1. They nicely cancel out each other. You have 2x1 to the power of 2. You don't have the other term. Again, if you start with x1, x2, you need to have minus x1 to the power of 2 or minus, and both minus x2 to the power of 2. They can be multiplied by some constants to claim asymptotic stability. Here we cannot. Basically, we only have Lyapunov stability, meaning that x1, x2 are bounded. Let's see if we can do more than that. Let's look at Barbalat's lemma. Let's look at v dot dot. V dot dot is minus 4x1 multiplied by x1 dot, which is minus x1, x1, x2. Here we know x1 and x2 are bounded, so this is bounded multiplied by another bounded signal. This is bounded, bounded. Everything on the right hand side of v dot dot bounded. So this guy is bounded, then this guy goes to 0, which is this. Then from Barbalat's lemma, as limit goes to infinity, x1 equals to 0. So this was another non-trivial, if you wish, form. We have x1, x2 bounded plus x1 goes to 0. And now let's consider another example. All right, so in this case, let's have x1 dot equals to minus x1 minus 2 x2, x2 dot equals to x1. Let's consider the Lyapunov function candidate v x1 to the power of 2, 2x2 to the power of 2. Why not? So it is positive definite, contains the origin, radially unbounded. And v dot is basically 2x1, x1 dot plus 4x2, x2 dot. Inserting equations here, 2x1 minus x1 minus 2x2 plus 4x2, x1, 2x1 to the power of 2 minus 4x1, x2 plus 4x2, x1. They cancel out. We only end up having 2x1 to the power of 2. So we have Lyapunov stability or boundedness of x1 and x2. All right, let's see if we can do more than that. Let's look at Barbalat's lemma. V dot dot is nothing but minus 4 minus 4x1 minus x1 minus x2. All signals here are bounded. Then v dot dot is bounded. So in addition to the boundedness of x1 and x2, Barbalat's lemma tell you limit t goes to infinity, x1 is 0. Now, can we do more than that? The reason I am saying that, let's look at this system, right? You can write this system as x1 dot, x2 dot, which is minus 1, minus 2, 1, 0, x1, x2. Let's call this matrix A. If you look at the eigenvalues of this matrix are negative. They have negative real parts. So we know from the solution, again, we can cover the solutions maybe in a different video. We know x1 and x2 going to 0. At least we said x1 can go to 0, but can we do more than this? To do a stronger version of Barbalat's lemma is LaSalle invariance principle. Now, LaSalle, connected with Barbalat you can use, tells you the following. Now, okay, x1 goes to 0. Now, what happens when x1 goes to 0? Let's look at the first equation. When x1 goes to 0, x1 and x1 dot 0. So from the first equation, x1 dot, let me write it here, minus x1 minus x2. This goes to 0, this goes to 0. When they are 0, x2 going to 0. So we can also say limit t goes to infinity, x2 is 0. In this case, we recovered global asymptotic stability. So, we started with this. Thanks to Barbalat, we showed this. Thanks to LaSalle, we showed this. And again, you can read LaSalle from books. I mean, the main idea is the following, right? So what happens in this case? Or simply, you don't need to recover. You don't have to do like this as well. you can start LaSalle from here, right? So when x1 goes to 0, when x1, let's look at the possibility of this. What happens when v dot exactly equals to 0? When v dot exactly equals to 0, x1 is 0. When x1 is 0, this is 0, this is 0, so x2 is 0. When x2 is 0, this is 0, so x1 is 0. So from LaSalle's invariant principle, x1 and x2 going to 0 when this is 0. Again, the last part, last couple, 1 or 1.5 minutes, what I said is important. You can rewatch, send a comment, I can explain more. This is the practical application of LaSalle. So you cannot use, I mean, you can use LaSalle's invariance principle in the previous examples as well, but it won't get you anything more than what we got. What I mean by that, let's remember for example, the previous example. What we had was, we had x1 dot equals to minus x1 minus x1 x2, x2 dot equals to x1 to the power of 2. We showed x1, x2 bounded, and x1 going to 0 as t going to infinity from Barbalat. And we had this Lyapunov function, right? Minus 2x1 to the power of 2. Now, let's see what happens when v dot equals to 0, x1 equals to 0. When x1 equals to 0, okay, you can say x1, x2 equals to 0. Second equation, x1 equals to 0, x dot's motion stops. So you cannot conclude x2 also goes to 0. You get some additional property from LaSalle, x1, x2, 0. Okay, I mean, good to know. But remember, x1 will go to 0. This is remain constant. It doesn't mean x2 to go to 0 as well. All we know, x2 is bounded. So LaSalle's invariance principle sometimes work that you can show global asymptotic stability from the Lyapunov function. So my main recommendation is the following. When you have a case like this, right, we had several examples on this. Try Barbalat to see if you can get more from Lyapunov stability, and then also try LaSalle to see again, can you get anything more than Lyapunov stability. Sometimes, like our example, we can record asymptotic stability. All right, so my last example will be about boundedness and global exponential stability. Let's say let's have x1 dot is minus x1 minus 2 x2. x2 dot equals to x1 minus x2 plus some constant disturbance d. You can have a time varying disturbance here as well, as long as it is bounded, everything will work just fine. All right, let's have v equals to x1 to the power of 2, x2 to the power of 2. Now, if you put things inside, right, if you differentiate it, if you take its time derivative, after several steps, you are going to get this. x1 to the power of 2, 4x2 to the power of 2, 4x2 multiplied by d. Now, when you had such terms, the common practice is to use Young's inequality, which is saying like something like this. If you have A transpose B, it is upper bounded by epsilon over 2, A transpose A, plus 1 over 2 epsilon B transpose B. I am going to apply this to this term because I would like to group terms depending on x2 to the power of 2. I can also live with that, but I don't want to. So this is upper bounded by epsilon over 2 x2 to the power of 2 plus 1 over 2 epsilon d to the power of 2. And here, of course, this Young's inequality holds for any positive epsilon, small or large. Sometimes you need to set it to a number in examples you are going to see. So once we do that, basically we have here minus 2 x1 to the power of 2 minus 4 minus epsilon over 2 x2 to the power of 2 and 1 over 2 epsilon d to the power of 2. Now I would like to give, I would like to set epsilon to 4 without loss of generality. When it is 4, then this term makes it 2. This is 1 over 8. So basically we have, and I apologize, when you use Young's inequality, this is no longer, you have this, you are upper bounding your function, right? All right, so now we have minus 2 x1 to the power of 2 minus 2 x2 to the power of 2 plus 1 over 8 d to the power of 2. Now from here I would like to get a structure like this. V dot small less than minus alpha v plus beta, with alpha and beta being positive constants, because if you have a form like this from comparison principle, you know, since this is not an, you know, this is a scalar equation, but it is not equality. If we have the equality, we know the solution, but since this is inequality, comparison principle says that, you know, this inequality's solution is upper bounded by e to the power of alpha t v0 plus beta over alpha. So it is very nice if you have beta 0, 0, you have global exponential stability. If not, you have boundedness. So it is of practice to write things in this form so that we can use comparison principle to conclude the proof in this case. Well, in this case, you can do multiple tricks. I am going to do one trick. I am going to drop, right? I am going to write this minus x1 to the power of 2, x1 to the power of 2, and going to drop one of the negative terms. If you drop, you are upper bounding it again. x1 to the power of 2 minus x2 to the power of 2, 1 over 8 d. So here we exactly have minus v plus 1 over 8 d to the power of 2. So in this case, alpha is 1, right? Alpha for our example is 1, and beta is 1 over 8 d to the power of 2. So in this case, basically v, or this, or v is this, right? So v x1 to the power of 2, 2x2 to the power of 2 upper bounded by e minus t, r alpha is 1, multiplied by v0. What is v0? x1 0 to the power of 2, 2x2 0 to the power of 2, plus beta over alpha. In this case, alpha is 1. So this is what we get finally. So x1 and x2 are bounded. After some time, basically the solution will be trapped on this circle in this case. So we have boundedness. So if your disturbance is 0, then you are not going to have this term. Then you have global exponential stability. Your x1 to the power of 2, x2 to the power of 2 will converge, will be less than or equal to 0 after this term vanishes. This means x1 and x2 are 0, and this is exponential stability with rate alpha when beta is 0. So basically you can predict in exponential stability settling time or convergence time is around approximately 4 divided by alpha seconds, whatever that alpha is. In this case alpha is 1, so I know after 4 seconds if beta is 0 or d is 0, x1 and x2 will converge to 0. Alright, so that's all. We talk about mainly, comparison principle, LaSalle, Barbalat, asymptotic stability, energy functions, Lyapunov functions, and I wanted to stay on the boundary of global. We can again cover local in another video. So let me know if you have any comments or any other topics that you want me to cover. We can go from there.